time at the end to maybe play Mind Trap or maybe discuss some probability, because I could hook our probability lesson before we even get there. But so you guys know, as we move forward, today I plan on 23.2 and 23.3. Oh, this is going to throw a wrench in gears if I don't teach tomorrow. We'll figure it out. But I'm trying to have us take our chapter 23 mastery next week, by next Friday, just so you're aware. Our mastery should be by next Friday, so make sure you're keeping up on all the homeworks. So your friend continues their study of shapes. No one decided to pass out notes. Your friend continues their study of shapes, and they're drawing shapes in the coordinate grid, and then she lays down her pencil and draws that other line that you see there. What do you think, especially after hearing my learning target, what do you think your friend is trying to do with that shape? Huh?
She's trying to get it onto the other side of the pencil.
What do you mean get it on to the other side of the pencil?
Reflect it.
Reflect it. Now, how do you think it's a reflection and it's not like a translation or a rotation or something like that?
Because it's being flipped around.
How do you know that?
Well, because they can see like if you if that was just like the paper and you fold it in half, then the shapes would match up.
Ooh, so that's a great point about reflections. If you fold, like quote unquote fold, if you fold your paper on the line of reflection, so imagine this is my line of reflection, right? If I fold my paper over, that shape should line up on top of the other shape. Because if I did a translation, my shape would stay pointing the same direction, and this line right here would not be part of my shape. So if I reflect this, the bottom of my shape should flip and just come out here, but this diagonal line, my hypotenuse here, will flip over that line of reflection and go right there. So if we continue that line of reflection down to one of the shapes that we had previously, if you go check your notes from 23.1, we have these shapes, our translation. So you might want to notate from here to here was a translation. Not translation, translation. But now I want to take this figure. What is this, by the way? What kind of shape? Trapezoid. Looks like a trap, if you've ever seen like a live trap. I want to take that shape and reflect it over the line of reflection that we have drawn right there, one box away from it. So go ahead and try that on your own. Reflect that trapezoid over your line of reflection. The problem is going to be if we do our probability hook and somebody wins the bag of suckers. I haven't thought that far out. Far out.
We have to go buy another bag of suckers.
Yep. James is like, how do I win? How do I win? So, anyone come up and drop? Anyone confident? Zach, come on up. Wait. Very, very close.
Goes like
Yeah, that's better. So, what do you notice about the vertice points or the vertex points? Like this point. What do you notice, Shahid?
At the same place but on the other side.
It's at the same place, but on the other side. Same thing with this vertice over to here. They're all one away. Any vertice that is 2 away from your line of reflection in the reflection is 2 away from the line of reflection. So reflections are very nice and easy because all they do is take your shape and flip it, and they keep things equidistant from that line of reflection, just on the opposite side. So you might then also want to notate that although up here we had a translation, now we have a reflection. So the key concept to our reflections is exactly
A
what we just
reflection
talked
or
about. That's why I'm just going to breeze right, well, I can't breeze exactly through this. Actually, I'm just going to pull up your notes. It's better to just refer to this. Any point that's being reflected when we start is our point. When we reflect it is our what point? What do we call those points? After we do something to it, like it's now going to be a prime. So wait a minute. Why is A and A prime in the same location? Why are, I guess I should say proper grammar, A and A prime in the same location? Noah?
Because they're on a y-axis, so it wouldn't be. I don't know how to explain it.
How far away from my line of reflection is point A? 0. How far away should my prime point be?
0.
Exactly. So this is reflected, but it's actually in the same place when it's reflected. So if you start on the line of reflection, you end up on the line of reflection. Notice that B is 3 away from my line of reflection. B prime is 3 away from my line of reflection, just on the other side. So that is the whole point of reflections. They are equidistant. And when I draw this line, this dotted line, it has to have a right angle. So obviously we're not going to draw a line like, you know, oh, let me go on this line and reflect over it. No. If you are reflecting, you're reflecting square.
Wait, so you can reflect on the x-axis too?
You could. You can choose any line of reflection you want. Here my line of reflection is the y-axis.
Oh, okay.
Because you can see my B and my B prime are equidistant from that y-axis. So, what type of transformation do we see here? Remember, transformation is the general, any sort of manipulation to my figures. So when I look at, sorry, this should be off. When I look at ABC, going to A prime, B prime, C prime, my points stay relatively where they're supposed to be. C's at the top, A's in the middle, and B's down at the bottom. What sort of transformation is that, Peyton? If it's a reflection, what's your line of reflection? It's not. Why is it not?
Because the C is 3 away and the C prime is 2 away.
But what if my line of reflection was at like 1/2? Then C would work if I made my line of reflection at 1/2. But then A and A prime don't work, and B prime wouldn't work. So for A and B, my line of reflection, actually for only A, B wouldn't even work there. B's line of reflection would have to be at -1/2. C's line of reflection would have to be at +1/2. This doesn't work at all. So what kind of transformation is this? Do we have a name for it? No, we don't know. So it's not anything that we know. Actually, you could even just put a question mark. It's a manipulation of the shape that doesn't even keep the shape the same. Now, if the points were labeled differently, we could actually make this a rotation and a translation. But I won't bore you with how. Actually, I will really quick. Imagine, so A to C, we go up 2/2, right? A to B goes down 2/2. A to B on the original goes down 2/1. A to C, or A prime to C prime goes up 2/1. So if this was C and this was B to start, then we could make it a rotation and then a slide, a translation. But it's not, so it's not. Shahib, what about our second one here?
It's a reflection.
It's a reflection. What's your line of reflection?
The y-axis.
So we would say reflection over the y-axis. And we can check that by drawing that line of reflection. C starts 3 away, C prime matches. A starts 1 away, A prime matches. B starts 2 away, and B prime matches. Every vertex is where it's supposed to be. I know it's a reflection. I don't have to check the shape any other way, because if my vertexes match, the shape has to match. Zach, what about my last one up here?
Would it be a translation?
Let's check it. If it's a translation, every point has to do the same thing. What did, not C prime to C. What did C do to get to C prime?
It moved to the left.
Not 4.
Wait. 3.
Yeah, it went to the left 3. Does A go to the left 3?
Yes.
Does B go to the left 3?
Yes.
Yeah, so this is a translation. Now let's put this in arrow notation. Did my X change or did my Y change? My X changed. What would happen to every X value here?
It would go down.
It would go down by how many?
-3.
Ooh,
Or
not it goes down by 3.
Yeah.
Or you could add -3, but you can't do both. So X minus 3, Y stayed the same. So we could also, instead of just saying Y, we could say Y plus 0 to show it did not move vertically. It only moved horizontally. Questions, comments, concerns? All right, try the got it. If it is a translation that we know how, or if it is a transformation that we know how to call it, tell me what it is, and then identify which of these show a reflection across the x-axis. We can also say across instead of over. So which of these shows a reflection across the x-axis? This one's a little weird. Start to have to get creative with how you look at things. James, what do you think is happening in that first one? Are we reflecting the x-axis?
No.
No. Are we doing anything that we can, like, state?
Translation.
Translation how?
The X doesn't change at all.
Okay.
And then the Y you do +2.
Ooh, not +2. We go down. Because we start at our original point, D, and go to D prime, always have to start at your original point. Guys, on your homework, this is where the most mistakes happen. People go from prime to original instead of going from original to prime. You gotta go from the original to the prime. Olivia, what about the second one here?
I think that's, that's a reflection.
But what is it a reflection over or across?
The y-axis.
Yeah, this is a reflection across the y-axis. Because D is 1 away from the y-axis, D prime is 1 away. E is 1, 2, 3, 4 away. And E prime is 1, 2, 3, 4 away. F is 3 away, and F prime is 3 away. They're all in opposite directions, so it is a reflection. Is that a question?
No.
Comment?
No.
Okay. Concern?
No.
Is that even a hand?
No.
Well, it is a hand, but...
Well, it's just
Ah.
no.
Ashton, last one here. Is this a reflection across the x-axis?
Yeah,
But wait,
not really.
this starts below and that is above, and like what is going on?
Sorcery.
Sorcery? Well, I don't know. Math can normally be explained by better terms than sorcery.
Incorrect reflection.
Ask yourself, is every original point the same distance away from the x-axis as the prime point in the opposite direction? Seth?
Yes.
How do you know this? What is the point that goofs us up when we're trying to look at this? What point screws with us?
F and F prime.
F and F prime, right? Because F starts below and F prime is above, which is the opposite as my other. So D originally is 3 above, D prime is 3 below. It works. E is 2 above, E prime is 2 below. It works. F starts 1 below, F prime is 1 above. Yes, this is a reflection across the x-axis. I cannot spell today. I'm sorry, guys. Reflection across the x-axis. Do not get confused when your shape crosses the axis to begin with. If you say we're going to make this pole, this like electrical conduit, the line of reflection. If I start here and I reflect, I go all the way to the other side. But if I start here and reflect where part of me is across it, I'm still going to have part of me across it, just the other way. Does that make sense? So don't get confused when they overlap. That's where a lot of people are like, what do I do? Because you're used to the shapes being in two different locations. They're allowed to overlap. It's okay. So this is exactly what it's showing. Notice that whatever axis you're reflecting across, so we're reflecting across the y-axis here, right? What happens to my points? Do the y values change? If I'm looking at my points and I'm looking at the y values, do those change from the original to the new? No. So when I reflect across the y-axis, my y values stay the same. What happens to my x values from my original? Oh, come on, I want green. What happens from my original to my prime? From -1 to 1, -3 to 3, and -2 to 2. Peyton? So you could say the x values are the blank of what they started with. You couldn't just say positive, because what if I crossed the axis? How do you compare positive to negative? Those are blank values. You're mumbling. Lily?
Are they opposite?
Yeah. So my x values become the opposite. X values become the opposite. Because if you're equidistant from the axis, you're just the opposite. Equidistant from the axis gives you the opposite values. So when we reflect the y-axis, the y's stay the same. When we reflect the x-axis, the x's stay the same. Pranav?
I just have one question.
Okay, I have one answer.
Okay, so if it's is this like not like I don't think this is like part of the topic, but
Okay.
like say if it's like there's a z-axis, would you also be able to reflect on that?
Yes, but then, so not every time we reflect are we going to reflect across an axis. So if we're not reflecting across an axis, the rules get a little bit harder, which actually is an amazing segue to this example. Draw the line of reflection. It is not an axis. Then, once you draw that, I want you to notate at least P and Q, and you can do all of them if you want, but where they start and then where the prime points go to. Seth, where is my line of reflection?
It's in between Q, the line in between Q.
So would it be a y equals line or an x equals line?
Y.
Remember, y equals lines are horizontal because that is the constant y value. So my line of reflection here is actually at x equal to 1. So somewhere off to the side, I want you to write that your line of reflection is x equals 1. That's how we would state where our line is. because on that line, my x values are always 1. An x equals line is a vertical, which is also why this is not a function, but you guys will get there later. The functions and not functions. And like Seth identified, these are equidistant. That starts 3 away, and that's 3 away. But when I look at my p prime point, say that 10 times fast, -2 and 3. So my y values are not changing, but my x values are. So this becomes 0, 1. My r prime becomes -3, -2. And my s prime becomes -5, 0. So if I were to try to make a statement of how I go from my x, y to the prime points, well, I know that we talked about opposite values, right?
Is it x minus? No, wait, that wouldn't work. Never mind. Yeah, never mind.
Zach? So my y's are staying the same, right? So I could go ahead and say y. It's going to be y.
X minus 2 or x
You're very close.
plus 2?
You're even closer now. Think about the fact that reflections involve opposite values.
Plus 1.
Oh.
Check if it works in every x situation. I'll give you a hint. We start by taking the opposite value, but then what? So the opposite of 4 would be -4, but then what do I have to do to get to -2? Nate? Plus 2. So then check, will -x plus 2 work in each other one? Opposite of 2 is -2, plus 2 would be 0. Opposite of 5 is -5, plus 2 is -3. Opposite of 7 is -7, plus 2 is -5. This works. How in the world can I get that plus 2? Where does that come from and why? Well, how far away is my line of reflection from just being the axis? From being at the axis, how far away is my line of reflection? It's 1 away, right? My x equals 1. But when you reflect that distance of 1,
It's plus, or well, it's moving to.
kind of gets like doubled, right, in a way. Like
Well, it
instead of
moves-
being 1 over here, because instead of going all the way, if p reflected on the y-axis, 1, 2, 3, 4 to get to the y-axis, it would go 1, 2, 3, 4 away from the axis. So my p prime, and I'm going to call that p double prime right now, if my y-axis was the line of reflection, it'd be way over there. But since it's not, and since my line was x equals 1, the distance from the axis gets doubled. I should really put the dot for multiplication. Times 2, and that is what tells me the difference from the opposite. So however far, if it's still horizontal or still vertical, if it is parallel to the axis, but not the axis, we can figure it out by doubling the distance from the axis. So plot these points. Do you guys think that we could reflect on the x-axis and then reflect on the y-axis? You think you got this? All right, let's skip these. Anybody feel like passing out notes for me so I can pull this up?
Sure I do.
that would be wonderful.
Are we doing our hook in the probability?
No, we're going to do rotations really fast. I'd like to do that when we start the probability lesson. Just to,
Is that next?
what do I have planned for it? We're going to get to probability. I promise you. I have it planned. We're going to do similar figures, then we're going to do probability. So we're going to do congruence, finish this chapter because we're congruence. Then we're going to do similar figures, which is very similar to congruence, except then you change size. You don't change what the shape looks like, but you change the size of it. Then we'll go to probability. We're kind of doubling back. So you have this image that's been working. And now your friend draws this square. And then they draw this line right here. And they tell you it's not a translation. It's not a reflection. And judging by the names of the notes, you can probably guess it's going to be a rotation. So when you rotate objects, what's another way to talk about rotations?
Turning.
Yeah, you turn it, right? A rotation is just another name for a turn. Thank you. So, when we turn, we have to turn about something, right? What can you do in basketball that does not get you called traveling? You can pivot, right? When you pivot, you're pivoting on what? 1 foot. That point is your center of rotation. When this foot stays where it is and my body turns around it, that's my center of rotation. So here, we have this point as my center of rotation. So if I'm going to rotate my square around that point and end up using this side, then I probably guess that this will come here. It has to still attach if it attached originally. So go ahead and finish out that square on your paper. Now here's the weird thing. If I labeled this A, that's a D, A, B, C, D, C is going to stay the same point. But where does B end up? Where does B end up? Baylor?
In the bottom left corner.
In the bottom left, because if this entire shape rotates and the amount of degrees that we're going is actually 180, every point will rotate 180 degrees. So point B starts top right, it ends up bottom left. A starts top left, ends up bottom right. D starts bottom left, it'll end up top right. So notice that, sorry, and these should all be prime points. This is C and C prime in the same place. That's B prime and this is A prime. If you perform a 180 degree rotation, everything's in the exact opposite location it was before. If it started bottom left, it goes top right. If it starts top left, it goes bottom right. So we switch everything, but that's because 180 degree rotation is one of the easiest there is. It's the 90 degree rotations that mess with us. But we will talk about the rules and the easy ways to remember these during this lesson. So our rotation, obviously, that's what we're talking about. That's a keyword here. We have to have a center of rotation, that point that we pivot around. And the angle of rotation is how far we've gone. So like I just said in the intro, we just had an angle of rotation that was 180 degrees. Every point was exactly opposite from where it began. Another way you can figure out this angle of rotation is draw a line through your center of rotation from the original point to my end point. How much rotation is happening here? 180. We can see because this is a straight line. If I had started here like it's showing and rotated all the way down around here, so this was my original and this is my prime. So you can go ahead and draw your original on here. So if I draw my original, it was, actually I'm not going to use blue. It was here to here to here to here. And then we applied a 180 degree rotation. What direction did we go? Clockwise or counterclockwise? counterclockwise. Is that a positive or a negative rotation? This is where math gets screwy versus the real world. A positive rotation is counterclockwise. Say it with me. A positive rotation is counterclockwise. Trust me, on your homework, that's going to be very important. If they tell you to rotate 90 degrees, they're assuming you're going the positive direction, which is counterclockwise. Don't ask me why. The big thing is our quadrant names. What quadrant is top right?
1,
What quadrant is top left?
2,
2, 3, and 4. Roman numerals. Don't know if you guys have learned those yet. This is why it is the positive rotation. We're working our way around our quadrants. When you guys learn about the unit circle up in Math 2, this comes back into play more. But the clock was not made based off our coordinate grid. And the reason this goes, I just said it, now I can't think of it.
counterclockwise.
No, sorry, which section it is. Quadrant.
Quadrant.
The reason this goes like that is this is positive, positive. This is negative, positive. This is negative, negative. And this is positive, negative. So that's why we go around this direction. My y's stay negative, my y's stay positive at first, then everything's negative, then my x's become positive again, and then my everything becomes positive again. Zach?
So to go clockwise, would it be like a negative?
Yeah, a clockwise rotation is in the negative direction. So, which of these shows a rotation about the origin? Now, here's what we're going to learn as the hockey stick method. This I stole from Mr. Hall. When we're going about the origin, so I want you to underline, highlight something about the origin, I can figure out how do I get back to the origin. Well, from F is easy. I go down 1, right 1. So I kind of draw my hockey stick. Now I'm going to not use F. I'm actually going to use D because it's easier to tell. I go down 4, right 2. To get, because I can't draw straight lines on the smartboard. It's just how the smartboard pixels pick it up. It's very hard to draw straight lines. To get to my prime point, I go 1, 2, 3, 4, and 1, 2. Again, to get from my original point E to my center, I go 1, 2, 3, 1, 2, 3, 4, and now I go 1, 2, 3, 1, 2, 3, 4. You can also compare your XY coordinates. Who thinks this is a rotation, that first one there? And we can do F. We go 1 and 1, and then we still go 1 and 1. Not a reflection, because E would have to be closer to... So we'll come back to that. Let's move on to my next one. Let's try our hockey stick method. I go 1, 2, 3, 4, 1, 2. So I should do the opposite out. So like my red one had shown. But now I go 1, 2, 1, 2, 3, 4. Now wait a minute. That doesn't look like my hockey stick rotated. Think about, so a hockey stick, right? Kind of looks like this. We are now talking about a hockey stick, quote unquote, as being a right angle. So my blue hockey stick to my red hockey stick, does it look like it rotated? What's it look like it did? Looks like it reflected. Let's try E. To go from my original, then to go to my prime, does it look like my hockey stick rotated? Mm-mm. So this is not a rotation. This is what?
That one
It's not a this is a reflection. It's a reflection here.
So it is a rotation.
Does this look like a rotation?
No.
Looks like
Can you figure out what it is? Bailey?
It's translation because the x-axis is staying the same, but the y-axis it's just moving down.
Move down, move down, move down. This is a translation down. How far? 1, 2, 3, 4, 5. So, come back here with a new outlook. Hang on to it for just a second. D to the origin. And this is when colors come into play very nicely. I go 4 down, 2 right. From the origin to D prime. Actually, so I'm drawing that wrong. I should here to here. Does it look like my hockey stick rotated if I keep it fixed on that point? Because realize, draw first coming off the origin. So whatever line you drew first coming off the origin, you want to draw that first. So I'll correct I'll correct myself on E. Actually, I'm going to do E differently. I'm going to come over, then down. So first thing I would need to do then, if I rotated, think about if I rotate down, this line that is now y-axis flops down and becomes x-axis. So now, choose green instead of red. I go over and then down. Does it look like that hockey stick rotated?
Yeah.
Yeah, because this blue line right here to this green line right here spins down 90 degrees. And we could do the same thing with F to F prime and see that it is. So this is our rotation. And it is 90 degrees in the positive direction. Yeah, she.
Also, it has to be a rotation because the question says which graph shows a rotation, and we did the other.
Elimination method, right? But the curveball is in math sometimes. And Mr. Hall and I were discussing this yesterday. Sometimes we'll throw you a problem. So be ready for this when you have math with Mr. Hall next year. He will occasionally hide wrong answers or unanswerable questions, like a question where all of the answers, none of them are right. We'll occasionally hide those in our practice or our mastery work. So we want you to really analyze, and if you really think none of them are, you would just say none of these are rotations. If you really thought none of them were rotations. So there is always that curveball possibility that it's kind of like a trick question in a way, but I don't like the word trick. So we can also check rotations by checking the angle. From the origin, assuming the origin is our center of rotation, notice it says about the origin. We could see from the origin to my original point, then from the origin to my prime point. So notice I have A prime. How many degrees is that from A prime? If the origin is the center of my rotation, my protractor sits down on it.
90 degrees.
90 degrees, right? It makes a right angle. Then we would turn the protractor and go C. That's terrible. Get rid of that. I'm going to go B. It's easier to draw. B to B prime. Does that look like a 90-degree rotation? Let's try C to C prime. C to C prime. Does that look like a 90-degree? Yeah, if I physically had a protractor, I could be turning it to check all these. But this is a 90-degree rotation because from my original point to my prime point with the center of my protractor at the origin, they all come out to be 90 degrees. And notice again, that's positive rotation. It's going counterclockwise. So if we put a protractor center on the origin and went to my original J and then went to my J prime, how many degrees would that measure on the protractor?
180.
180, right? Try it with your K. Center on here, go to K first, Then go to K prime. How many degrees would that measure?
180.
180. I don't know where we got that accent from. What about O? Point O, does that show 180 degree rotation? Lily's nodding her head. Lily, why did O not move?
Wasn't that the thing that it rotated on?
Yeah. It starts on the center of rotation. If you start on your pivot foot and you say, where did my foot move? Well, my pivot foot didn't go anywhere. My outside foot went a lot of places, but my pivot foot does not move because it's on the center of rotation. I'm going to end up making holes in my carpet here. Is this making sense? Do we have any questions or concerns? So notice this rotation from B to B prime. What sort of angle does this look like?
90 degrees.
So I could phrase this as a 90 degree positive rotation or not 90 degree positive, my bad, 90 degree negative or 270 degree positive. If I go from B to B prime, the positive direction, it's actually 270 degrees. So a lot of people come back the day after I send this homework and they're really mad. They're like, I kept getting these wrong. I was answering 90 and it would tell me it's 270. You've gotta realize positive rotations counterclockwise. So although it looks more efficient to say this is a 90 degree rotation, that's in the negative direction. We have to phrase it in the positive direction. So we would use 270 unless we specifically say negative rotation.
So if you put a question on homework, it'll say, like,
What is the degrees of rotation from the original figure to the prime figure? This answer will be 270 degrees. Because we assume positive unless we're told otherwise.
But is there any questions where you ask, like,
For negative rotation, I haven't put it up yet, so I'm not certain. So we're out of time today. We will start Monday, because I won't see you guys tomorrow. We will start Monday by taking any questions from this lesson that you guys have, and then we will move on through the rest of our chapter fairly quickly. So you have all tomorrow and all weekend to get this taken care of. I've also been told that you're doing a web quest tomorrow in language arts, so I think if you get that done early, you'll have time to work. So, hopefully, there's not a ton of rush to get this homework done. You have the weekend and whatever.